Now we're going to take a look at vector addition and applying right triangles. So let's say we had these three vectors. We have vector A, vector A represents 3 miles to the north. And we want to know, what does vector B represent and what does vector C represent? So if we look at vector A and we look at its length, the length here, you know, it's about, we have 1, and this is a full length here, this is a full length here, this is a full length, so at least 3, and if we add up this and this, we almost get 4. So 4 boxes represents 3 miles. So if we look at B, we could use that to scale. We know that it's definitely more than 3 miles, and it's representing some to the east. And then for C, it's even longer than B, vector B, in terms of length of miles, and then at a certain angle theta here. So equal vectors have the same length and direction and can represent the same quantity. So what I want you to do is go ahead and draw a bunch of equal vectors, same length and same direction. So for mine, I just drew vectors like this. These are all equivalent vectors, and you can move vectors from place to place, and it doesn't change what that vector represents. It's still the same length and same direction. Okay, now we're going to apply some of the right triangle trigonometry that we've been using. So we're standing at the very top of a tower. Notice that in order to see a manhole cover 50 meters from the base of the tower, you must look down at an angle of 75 degrees below the horizontal. If you're 1.8 meters tall, how high is the tower? So let's go ahead and draw the situation. We have our tower, we're standing up here, and we have a manhole cover down here, we'll say, and we're looking 75 degrees below the horizontal. So this is the horizontal. Say we're looking below the horizontal down here, and this angle is 75 degrees, and we know this length is 50 meters down here, and we want to figure out how tall the tower is, and we are 1.8 meters tall. So yeah, go ahead and pause the clip, see if you can figure out how tall the tower is, and when you're ready to resume, you can hit play. Okay, so hopefully you recognized here with this is the right triangle right here. We have an angle of 15 degrees taken away from 90 degrees there. This is the hypotenuse. This is the opposite side over here. This is the adjacent side. So we could use the tangent. The angle is 15 degrees. The opposite side is 50 meters. We're looking for the adjacent side, so we'd have to cross multiply first. So the tangent of 15 times the adjacent is equal to 50. Divide both sides by the tangent of 15, and we get 186.6, but we have to subtract out our the height of the person. So this is the actual height right here, 184.8 meters. Okay, so next we're going to take a look at a driving situation where we're driving up an incline road. After 1.5 miles, you notice the signs along the road indicate your elevation is increased by 520 feet. We want to find the angle of the road and then how far we need to drive to gain an additional 150 feet. So let's go ahead and draw the initial situation here. We've got our road, driving up the road, and after 1.5 miles, we have an elevation increased by 520 feet. So let's say that's here, and we start out here. So what we can do is take a look at this. Here we know that we went up by 520 feet, so 520 feet, and we know the length of this is 1.5 miles, which we're going to need to convert to feet. So I have the conversion up here. And we want to know what the angle of elevation is. So you're going to want to set up your right triangle, figure out your lengths, and then go ahead and try part B as well. See if you can get the additional, how far you would have to drive for an additional 150 feet of elevation. This is a good practice to see if you can apply some of that right triangle trigonometry that we looked at. So go ahead and pause the clip and give that a shot, and then you can look at the solution. Okay, so when we convert, we should get 7,920 feet as the length there. And in this case, we know the hypotenuse and we know the opposite side. So we can use the inverse sine function, and that'll give us an elevation or angle of 3.764 for the incline. Now for the second portion, we know the angle now, and we have an addition 150 feet here, elevation increase. So we can again use the sine function to figure out how long the hypotenuse would be, which is how far we would have to drive. So we have the angle here, sine of 3.674. We have the opposite side length, and we're looking for the hypotenuse. So this is the additional length that we would need to travel. Okay, something else that's going to be really helpful for us as we look at this is breaking up vectors into x and y components. And so we know with vector addition, if we break things up into components, we can determine, or we can break them apart and then bring them back together, and it's the same thing. So in this case, we want to find the x and y components for this vector. So east is where we start. So we'll go ahead and put our coordinate axis here. East is where we start, north is where we go. So we're going to go up 55 degrees. It should be a straight line. Then we're going to break this into the x and y components. So in other words, we could go this much over, that would be our x component, and then this much upwards, and that would be our y component. So if we look at the angle here, this is 55 degrees. 55 degrees. And if we wanted to find the x portion here, let's write down what this is. So this is the adjacent side, this is the opposite side, this is the hypotenuse. So if we write out C7aa, to get the adjacent side here, we would need the cosine function. So cosine of 55 equals the adjacent is what we need over the hypotenuse, which is 175. We could cross multiply, and the adjacent side comes out to be 100.4 meters. So that is how much in the x we have. And then to find the opposite side, here we can use sine, because we know we're looking for the opposite side. We know the hypotenuse. So the sine of 55 equals the opposite over the hypotenuse, which is 175. We cross multiply the opposite side, sine of 55 times 175, 143.4 meters, and so that is how much in the y. And so if we add those two vectors together, we go to the east by 100.4, and then we go north by 143.4. That would be the same displacement as the overall vector. Okay, so why don't you go ahead and try this one. Draw out the coordinate axis, draw out the vectors blank of blank, or the vector itself, and then solve for the x and y components. Make sure as you draw this, you draw the tail to tip with the vectors. So yeah, go ahead and pause it, and then hit play when you're ready to check your answer. Okay, so we start on east and we go south by 25 degrees. And we can solve for the adjacent side. So this is this side right here. So the arrow would be like this. We would go, this would be our x component, 31.72 kilometers east. And then to get the opposite side, which the arrow looks like this, it's going downwards, we can use the sine function, and this would be south. So this would be east, this would be south. Those two vectors like this and this will make up the resultant vector. So now let's say we have two vectors and we want to get a resultant vector. So we're going to go 150 meters west. So we'll set up our coordinate axis, and then we want to draw that vector first. So 150 meters west. And then from there, from the tip of that one, we draw the tail of the next one. We go 300 meters north. And then the resultant is from here to here. And we're going to describe that based on a length, so how many meters it is, and then how many degrees it is, blank of blank. So what I want you to do is go ahead and finish this. Go ahead and determine the length, the angle, and then describe it blank of blank. Okay, so let's see how you did. We can use the Pythagorean theorem. The Pythagorean theorem will give us a length of 335.41. And then our angle, we know the opposite side, we know the adjacent side. So opposite over adjacent inverse tangent will give us an angle of 63.43 degrees. And then we start on west and go north. So start on west, go north. So north of west, 63.43 degrees north of west. Okay, so I'm going to let you work this one all the way through. Draw your coordinate axis first, then draw each vector, and then describe the vector based on the length, how many degrees, and then blank of blank in terms of the coordinate axis. So go ahead and pause, and then when you're ready to check, you can hit play. Okay, so here is our, I should have drawn the coordinate axis first. So south, north, east, and west. So you should have drawn 120 up and then 72 over, and we can get the hypotenuse. And this should come out to be 139.94 meters at 30.96 west of north, because you start on north and go west by that many degrees. When we add vectors, the way we do this, let's say we had a vector A and vector B and we added them together, we use what's called the tail to tip method, where we place vector B on the tip of vector A, and then the resultant will be from the beginning of vector A to the final place where vector B ends up. So this would be the resultant. So it's not like we're not doing this if it's like 4 plus 3 equals 7. It doesn't work that way with vector addition. You're adding the vectors themselves. So it's a way that, and this is the graphic way or graphical way to do this. Mathematically, we'll work through that as well. Now, if we subtract vectors, what we do is we add the inverse of vector B. So let's say we'll first draw vector B, then draw vector A first, then draw vector B, so that the tail is on the head of vector A, and then we can draw the resultant. So A minus B would look like this. We have A, vector B. We would flip vector B, place it still on the tip of vector A, and then draw the resultant vector. So this would be vector substitution. Again, it's not a numerical, like a 10 minus 5 equals 5 something. It's not like that. We're adding the vectors themselves. Okay, so now we're going to add and subtract vectors. And so for this one, vector A points in the positive x direction, has a magnitude of 75 meters. Vector B has a magnitude of 30 meters, a direction of 30 degrees above the x-axis. So we're first going to add the vectors together, then we're going to subtract them. So if we draw out vector A to scale, we can line that up, and then we can draw vector B up at an angle. The resultant vector would look like this. Now, if we're going to subtract them, we have vector A. We draw the reverse of vector B, and then we can draw the resultant. Okay, so now what we're going to do is draw vector A, then vector B, then vector C, and then draw a resultant. So if we draw our three vectors here, we have vector A, then vector B, and then vector C, and we can draw the resultant. So now we're going to change the order and see what happens. So we're going to draw vector B first, then vector C, then vector A. Now if we do that, vector B, then vector C, then vector A, turns out this is the exact same vector. So what we can see here is it doesn't matter the order that we add the vectors. As long as we add the same ones, we're going to get the same resultant. So if we did C, then A, then B, here's C, then A, then B, again the same resultant vector.